Hi students, in today's session we are going to discuss about AFM, that is the atomic force microscope. Atomic force microscope is an important equipment used for the surface characterization of nanomaterials, that is for studying the surface structure of these materials. It is based on the scanning probe microscopy technique. As we had discussed in our previous session, in the scanning probe microscopy technique, a probe, which is usually a metallic tip, is placed just above the surface whose structure has to be studied, and uh, based on the interaction between the probe and the surface, which is monitored, we can determine or image the surface topography of the sample. So, AFM is a type of scanning probe microscope. In AFM, the interaction between the probe and the surface is the van der Waals force between the tip and the surface. Or in the AFM, we use a force probe to study the surface structure of the sample. So let us see a figure of this AFM. So this is the sample which has an uneven surface, and we have to image the surface. We have to get an image of the surface, or you have to study the surface structure of the sample. For that, see, this is the probe, force probe, which is a metallic tip, and it is attached to a cantilever. You must have learnt in your earlier classes a cantilever is a beam which is fixed at one end and free at the other end. At its free end, the probe is attached, or the metallic tip is attached. Now, the force of attraction or repulsion between this probe and the sample is used to study the surface structure of the sample. The sample is placed on a piezoceramic tube, and as this tip moves over the surface, as it goes over these heights and when it comes along these depressions, the cantilever suffers some kind of vertical deflection during the as it passes over the different topographical variations on the surface. ഈ സർഫസിലെ ഉയർച്ചകളും താഴ്ചകളും അനുസരിച്ച് ഈ കാൻഡിലിവർ ബീം പല രീതിയിൽ വെർട്ടിക്കലി ബെൻഡ് ചെയ്യും. Okay, depending on the bending of this beam or by measuring the angular deflection of the beam, the surface topography is measured. And here there is a laser and a photodiode. So this angular deflection of the cantilever is again measured accurately by using an optical lever. An optical lever means you allow a beam of light to fall on the cantilever. Depending on the deflection of this cantilever, the reflected image of this beam will be at different angles, and it is collected by a photodiode, which is then sent to the detector. Okay, so let's go to the detailed note. So we have discussed AFM is a type of scanning probe microscope. It is used to study the topography of the sample using a force probe. It operates by measuring the attractive or repulsive force between the tip and the sample. Now, the AFM works in two modes. One is the contact mode and the other is the non-contact mode. In the contact mode, the tip slightly or lightly touches the surface of the sample, and a repulsive force acts between the tip and the sample, and this force is measured. Whereas in the non-contact mode, the tip does not touch the sample, and the attractive force between the cantilever tip and the sample is measured to understand the surface topography. Now, as the raster scan drags the tip over the sample, some sort of detection apparatus measures the vertical deflection of the cantilever, which indicates the sample height. So as the raster scan drags the tip, raster scan means some kind of line by line scanning is done. Okay, so the tip moves over the sample line by line. So as the raster scan drags the tip over the sample, what happens? Our cantilever suffers vertical deflection depending on the heights and depressions on the surface. The cantilever undergo vertical deflection, and this vertical deflection is measured using a detector, and this indicates the sample local sample height, the height of the sample at that position. Okay, so I hope contact mode, non-contact mode, and how an AFM works is clear to you. Now, AFMs can achieve resolutions of 10 picometer, that is, surface depressions or heights as small as 10 picometer can be measured using an AFM. So, AFM can achieve a resolution of 10 picometer, and they can image samples in water and air. So these are the advantages of AFM. So AFM is an excellent equipment for determining the surface structure of a sample. It has a very low resolution of 10 picometer. 10 picometer means 1 picometer is 10 raised to minus 12 meter. So even a height difference on the surface of your sample, even a height difference in the range of 10 picometer can be measured using an AFM. So it has an excellent resolution. Now, how is this excellent resolution attained? AFM has a number of refinements that enables it to attain atomic scale resolution. അതായത് AFMന് പല modifications or refinements or some kind of attachments. It has some kind of some kind of modifications or attachments which are called refinements attached to it that helps to attain this atomic scale resolution. So these include sensitive detection using laser beam, flexible cantilever, sharp tips, high resolution tip sample positioning, force feedback, etc. are the refinements which you have together with the AFM, which enables it to attain such an excellent resolution. Now let us see what is the reason for the AFM to have to attain atomic scale resolution. One is the laser beam deflection. I told you already. Now when the cantilever deflects, in the figure, when the cantilever undergoes vertical deflection at the different positions on the surface of the sample, the cantilever tip will undergo, this cantilever will undergo vertical deflection, and a laser beam is allowed to fall on the cantilever, and it will be reflected at different angles depending on the angular deflection of this cantilever. And the reflected beam is collected by a photodiode, which is in turn sent to a detector. Now, since the length of the cantilever is very small and the distance between this cantilever and the detector is very large, so what will happen? The deflection of the cantilever is magnified several times in the detector. ഈ കാൻറ്റിലിവറിൻ്റെ വലിപ്പം ചെറുതും കാൻറ്റിലിവറും ഡിറ്റക്ടറും തമ്മിലുള്ള ദൂരം വളരെ അധികവുമായതിനാൽ V/U, that is the magnification of your cantilever deflection, is several times in this detector. ഈ ചെറിയ ഡിഫ്ലക്ഷൻ ഈ ഡിറ്റക്ടറിൽ വലിയൊരു ഡിഫ്ലക്ഷനായി കാണപ്പെടും. സോ ഈവൺ മൈന്യൂട്ട് ഡിഫ്ലക്ഷൻസ് can be noted in your detector because it will be seen in the detector as a big deflection. Okay. Why is it happening? Because the distance between the cantilever and the detector is about 1,000 times larger than the size of your cantilever. Okay. So the deflection of the cantilever is magnified several times in the detector, so that you will be even a very small deflection will be detected here as an appreciable one. So I hope laser detection. So that helps the AFM to attain a very low resolution. First point, laser beam deflection for sensitive detection of the cantilever deflection. So the laser beam is getting reflected or deflected. That helps in the sensitive detection of the cantilever deflection. AFM can measure vertical cantilever deflection with picometer resolution. For this, AFM uses this optical lever, that is a laser beam setup. The optical lever is operated by deflecting a laser beam off the cantilever. That is, the laser beam touches the cantilever and gets deflected. The reflected laser beam strikes a position sensitive photodetector using which the angular reflection of the cantilever is measured. Since the cantilever to detector distance is 1000 times the length of the cantilever, the optical lever greatly magnifies the motion of the tip. This is what I told you. Even a very small deflection or motion of the tip can be detected in the detector. The next refinement which helps to attain a very low resolution in the AFM is the mode in which the AFM cantilevers are made. The mode in which means the size of your AFM cantilever. The size and mass of your AFM cantilever is the second refinement in the AFM, which helps to attain very low resolution. Okay, so AFM cantilevers have a very high flexibility. It should have very high flexibility. That is, this tip must be highly the cantilever must be highly flexible. Otherwise, what will happen if the cantilever is stiff or rigid? The metallic tip will drag over the surface and damage or destroy the surface of the sample if this is not flexible, if the cantilever is not flexible. So the cantilever must be highly flexible. If the cantilever should be highly flexible, its spring constant K must be very, very small. It's usually 0.1 Newton per meter. Spring constant in the range of 0.1 Newton per meter. So, for a highly flexible AFM cantilever, the spring constant must be very low. Okay. But when the spring constant becomes low, that means the cantilever will take a very long time to image a surface by dragging over it. That is, the resonant frequency of this cantilever will be given by nu is equal to 1 by 2 pi root k by m. When k becomes small, the resonant frequency becomes small. That means the time taken to scan over a surface becomes very large. So what should be done? The spring constant cannot be increased. If the spring constant is increased, resonant frequency will increase. That means time will become low. Within a short time, you can scan over the entire sample. But you cannot increase the spring constant. If you increase the spring constant, what will happen? The flexibility of your cantilever will be lost and it will destroy the surface of your sample. പറയുന്നത് മനസ്സിലാവുന്നുണ്ട് എന്ന് കരുതുന്നു. അതായത് ഈ AFM cantilevers വളരെ ഫ്ലെക്സിബിൾ ആയിരിക്കണം. അല്ലെങ്കിൽ അതിന് മുറുക്കം സംഭവിച്ചാൽ എന്ത് പറ്റും? It will damage the surface of your sample. So to have high flexibility, the spring constant must have a very small value. But if spring constant is very low, what will happen to the resonant frequency of your cantilever? Nu will be equal to 1 by 2 pi root k by m. Since k is very small, the frequency will become very small. Frequency is very small means it will take a very large time to scan over your sample. The cantilever will scan over your sample taking a very, very long time. So what should be done? For the cantilever to scan over the sample quickly, your resonant frequency must be high. To increase the resonant frequency, K must be increased, but we cannot increase K. Then what should be done? K is small, but make your mass still smaller. Let the mass of the cantilever be reduced to such a small value that the resonant frequency is brought down. If resonant frequency is brought, if the resonant frequency is made high, that is, mass is reducing to a very small value, that nu is increasing. So when the resonant frequency increases, the time taken to scan over the surface will decrease. Okay, so what is done? We use AFM cantilevers which have very very small mass, or very small AFM cantilevers having very low mass is used, so that we can attain high resonant frequency yet maintaining the flexibility of the cantilever. I hope this is clear to you. So these are two refinements which are used in the AFM, so that it can attain very high very high resolution. I hope the session is clear to you. You have to learn about two more refinements used in the AFM. One is the tip of the sample, and the second one is, that is the tip of the cantilever, that is the the metallic tip that you use can be modified so that you can attain a very good resolution for your AFM. And the second one is this piezoelectric tube. Okay, this piezoelectric tube which is used, which is also a refinement which enables the AFM to attain a good resolution. So those two will be discussed in the next class. So I hope this session is clear to you. If you have any doubt, please do contact. Thank you.